All right. Hey everyone, welcome back to the stream. Um Today we'll be continuing with the Learning DSA series, and I believe it's the third stream. Also, I understand that my React JS stream was cut short off by a power failure, so I apologize for that. Yeah, I need to sort something out for it's just that sometimes the power flickers, right? And that's what actually happened right now. It was just gone for a minute, but even though my system was up and running, Wi-Fi went down and caused the issues. So yeah, let's see how we can sort that out. Anyhow, so let's do a recap first, and then we'll get back to our stream or learning actually, not stream. All right. So, as a recap for the DSA learning DSA series, this would be sort of like an unstructured course. Well, I should rather say a semi-structured course of sorts. So, last time we completed what's it? Time and space complexity. We covered a course on by obviously Freecode Camp. They have almost everything out there. Yeah, we covered a course by Freecode Camp, which taught us about big O notation, and we also know what big theta and big omega is, and we also know what all these runtimes are about, from constant, logarithmic, linear. There's also log linear till factorial. We also called out merge sort, binary sort. Believe binary sort runs in well, merge sort runs in log linear time, and binary sort runs in logarithmic time, right? So just confirm, because you're halving the thing each and every time, right? Yeah, it runs in logarithmic time, and this runs in log linear time. um Great. After that, we decided to come to problem solving techniques here. We covered what brute force was a bit, and then we started with backtracking. We found a video by, you guessed it, Breakout Camp, and they are covering a couple of backtracking problems here. So let's give this a go. And yeah, we went through a bit here, and was developed by um, Lin Sheng. I might be pronouncing the name wrong. I apologize in advance. Um, yeah, we found this. The overview. I haven't completed the course, yes, but at least the overview looks good. We found this excellent course by Lin here in Freecode Camp, and we were about to start this. She gave a interview, not interview, an overview of what the she has some sort of template or something, which we'll get to, and we post at the place. I believe she was, yeah, she's using lead code to solve the problems. So that's where I ended the stream. I went ahead and created a brand new lead code account. Yeah. Now I've used LeetCode before, yes, but I haven't used it as much as I've used CodeWars. That's my main go-to site when it comes to solving problems. But I guess LeetCode is in a way more what's the right word? More DSA like, whereas CodeWars is more gamified and just this is more. I guess what I'm trying to say is that LeetCode is more DSA sort of, if you know what I mean. Um, either how I mean either way. Let's start. Yeah, let's continue with the course now that we have a lead code account. I might link. I haven't. I realize I haven't linked my lead code and code was like profile in the description. Maybe I'll do that. Right. So let's continue with this. Also, I've just created a new folder, and this is what this is. I believe this is the approach we'll be also following for the other problem solving techniques. We'll just, you know, create a folder and put the problems in there, or I mean the solutions of the problems in there.
Row or the same column, we may just keep a 1D list that tracks
So let's see.
the n queens on an n by n board. For example, here we are placing 4 queens on. You can find this template in my.
You know what? Let's just start from here. I know we covered a bit, and let's just start from here just to get a more fresh perspective.
GitHub just links to in the video description below. Let's start with some keywords and concepts in backtracking problems that will help us understand the template better. The first keyword, state. Essentially, a backtracking problem is asking you to find valid states. Take the n queens example that we will solve later in this video. An example of a state is just arbitrarily placing n queens on an n by n board. For example, here we are placing 4 queens on a 4 by 4 board. Better.
Oh wait, I believe I kind of guessed what these functions meant. So let me just do that again. I know I already did it, but still. So we have is valid state, which okay, there's a obvious comment here. It checks if the state is a valid solution to whatever problem we're solving. Then we have get candidates, which I believe would, like, given a state, it would get all possible candidates for the next state from that state, if that sort of makes sense. Although I am guessing, so I may be wrong here. um then we have search function, takes state and solutions. Okay, so first of all, if the state is a valid solution, then we append to the solution, and I guess depending on the problem we might return. Like if you just want one solution, then I guess it makes sense to return here. Else let's just assume we just need one solution, right? And that means we haven't received the solution yet, so we get the all other like the next step, right? Or the next candidates from the state using the get candidates function. And then we wait, before I continue, let me just, yeah, I just want to check if both my audio were turned on. So what do we do here? Each candidate we added to, I believe state is a set. Then yeah, it's a set. We add to state, we add each candidate to state, then we search for state with solutions again. A solutions doesn't make much. Oh no, it does make sense, right? Huh. And once we get, like, let's say, okay, what's gonna happen here? When we do a search, either the current state is gonna be a solution or it's not gonna be a solution. Now, if it is a solution, we just remove the candidate from that state. State or remove candidate. What I can't understand is why. Oh, okay, that makes sense. Because if we do a search here and if it does return a valid solution, then we just return the solutions here, right? This function just ends altogether. But if it does want to, but let's say it was not a valid solution, right? Which means this for loop will run again. And what we're gonna do is we're gonna remove that candidate from the set because we already validated that candidate, right? So we'll remove it from the state and then we'll just resume. Okay, the function headers make sense in a way now. So let's begin. I mean, let's continue with the course.
The first keyword, state.
Wait, I'm hearing some sort of noise in my audio here. Let me just. Hello, hello. Let me just turn on my. Hello. Yes. Hello. 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 Yeah, it's so some noise there for sure. Let me just check. Be right back. Alrighty, I'm back. Sorry for that detour there. The audio should be clear now.
Essentially, a backtracking problem is asking you to find valid states. Take the n queens example that we will solve later in this video. An example of a state is just arbitrarily placing n queens on an n by n board. For example, here we are placing 4 queens on a 4 by 4 board. On the contrary, an example of a valid state requires that the queens are placed in a fashion that they cannot attack each other. If you aren't familiar with the rules of chess, don't worry. The moves of queens are pretty straightforward. A queen can move horizontally, vertically, or diagonally. Therefore, for a replacement of the n queens to be valid,
In fact, if you wanna, let me just check here. Yep. I didn't know this would be useful in my stream, but this is what a queen looks like. I mean, a physical queen looks like, I guess. But yeah, this is a queen, alright. And as mentioned, it moves horizontally, vertically, diagonally. It's the most powerful piece in the board.
they can't stand on the same row, the same column, or the two diagonals. So how do we construct a valid state like this? Well, we build up from previous states. Suppose we're starting from the blank n by n board where no queen is present. We can put our first queen arbitrarily wherever we want. Let's say we put it here. Then where can we place the second queen? You can see now our choices are limited, or in background terminology, our candidate states are limited. Because we place the first queen here, this entire column, this entire row, and the two diagonals are now unavailable for new queens. Let's say we just put the second queen here, where it's available. Next, we try to see where we can fit in the third queen. Our candidates are now more limited because we put the second queen here. This column, this row, and this diagonal is not available. So our third queen can only go here. Finally, let's place the fourth queen. Because this third queen is here, it blocks this diagonal, and this row and this column, leaving our fourth queen to stand here. Great. Now, is this global layout a valid solution such that no queen can attack each other? Well, we've already seen in our checks.
Yep,
So
it is.
we have found a valid solution to this n-queen problem. As a counterexample, consider if we place the first two queens like this. Now, all these cells marked in red are unavailable, and we only have one left for the third queen, and nowhere to place the fourth queen. This means that this succession of state searches fails to lead to a valid solution. And this is pretty much it about states, identifying candidates to build the next state, and validating a final solution. Now let's look at how these procedures are defined in our template. There are 4 functions in our template. The first 3 is valid state, get candidates, search, are helper functions. The last and most important one, solve, is the entry point to our program. The solve function is indeed the one that a LeetCode problem is asking you to write. It is responsible for returning the valid solutions. Let's look at the helper functions one by one. Is valid state. This function takes in a state and returns a boolean. It validates whether a state can be used as a final solution. In our queens problem, a state is a validated solution if all n queens are placed on the board and none of them can attack each other. Get candidates. This function finds a list of candidates that can be used to construct the next state. Search. This is a recursive function. It calls the previous 2 helper functions and checks if the state is a valid solution to our backtracking problem. If it is, it records the solution by making a deep copy of the state. Note that we do need a deep copy instead of a shallow copy because we will continue to modify the state as our search goes. But we need a static snapshot of the valid state here. This line of return search
We'll just go
This
back.
function finds a list of candidates that can be used to construct the next state. Search. This is a recursive function. It calls the previous 2 helper functions and checks if the state is a valid solution to our backtracking problem. If it is, it records the solution by making a deep copy of the state. Note that we do need a deep copy instead of a shallow copy because we will continue to modify the state as our search goes. But we need a static snapshot of the valid state here. This line of return is commented out because depending on the nature of the problem, we might need to find all valid solutions or just one. If we only need one, we can return as soon as we have found it. Otherwise, we continue on until we exhaust all the possible search states. Continue down here. If the state isn't yet a valid solution, we find candidates to build the next state. Recall that getCandidates return a list of candidates. For each one, we add the candidate to the state. In the queen's problem, for instance, suppose our state only contains the position of the first queen. Here we add a candidate position for the second queen. Then we take this modified state and recurse on it by calling the search method on this modified state. If the modified state is valid, the solution is recorded, like here. Otherwise, the search function fetches candidates for this modified state and recurs further. Eventually, for some state, there is no more possible candidate. Think that example where we cannot place a fourth queen anywhere because all the spaces have been occupied. After returning from the recursive search, we restore the modified state to the original by removing the candidate from the state. Returning from the recursive search, we restore the modified state to the original by removing the candidate from the state.
Say that again.
Where we cannot place a fourth queen anywhere because all the spaces have been occupied. After returning from the recursive search, we restore the modified state to the original by removing the candidate from the state.
In other words, we backtrack. Right. Alright.
Again, in the queen's example, we undo the placement of the second queen.
I guess that's where the name backtracking comes. I mean, backtracking comes from.
The first queen. As for solve, it starts with an empty list of solution and an empty state. It calls search on the state and this list of empty solution. Search will eventually fill up this list of empty solutions and then return the list of solutions. And remember, this is the function that the code problem is asking us to write. When using this template, keep in mind that this is only a template. So your helper functions is valid state, get candidates. They might take in additional parameters. Search might also return a Boolean indicating whether a solution has been found and return early if there is one and only one valid global solution, like in the Sudoku problem that we will eventually see. This concludes our brief introduction to the template. Next, let's solve the queen's problem hands-on in LeetCode.
Alright, we'll take up the problem here, but before that, let's give GitHub a visit. So which one is, maybe it's this. Alright, okay, well, we have the solution down there. So look at that, we'll code alongside. Right now, let's just create a new file, let's call it template.py. I mean, not by, it should be .py. And all right, this would be our template. Okay, cool. Let's go back. Let's open up this problem. I mean, we can just search for it, can't we? I think we can. I mean, it's a famous problem after all. So and queens. Ooh, all right, there's a second version. I guess there are, variations of n queens as n queens and n queens too. I'm just interested in what the problem statement for n queens 2 would be. Oh, it says return the number of unique solutions. Okay. Well, let's see. Yeah.
Here we are on LeetCode number 51, the n queens problem, which is a LeetCode hard problem. Let's first read the problem statement. Given an integer,
I'm gonna assume the text is just too tiny, isn't it? Let's see how I can. Yes, this is one way of doing it. Can I actually let's just read the problem statement here first. The n queens puzzle is a problem of placing n queens on a n times n chessboard such that no two queens can attack each other. Given an integer n, return all distinct solutions to the n queens puzzle. You may return the answer in any order. Alright, okay. Each solution contains a distinct board configuration of the n queens placement where q and dot both indicate a queen and an empty space respectively. So n equals 4 returns this output. Now what does this actually mean? The first one would be a solution, right? Oh, okay. So if we treat this sort of like an array, the dot represents that there's no piece here, there's a queen here, there's no piece here, no piece here, no piece, no piece, no piece, a queen, queen, no piece, no piece, no piece. Then we have no piece here, again no piece here, then we have a queen, and then we have no piece here. There are two solutions. We return this and this. For n equals 1, yeah, just having that queen on the square, this explains that. There can be a maximum of 9. N can go all the way up to 9. All right, okay. So far this makes sense. Now let's go back. I mean, I guess the video is in here, isn't it?
And we want to return all the distinct solution to the n queens puzzle, and we may return the answer in any order. And LeetCode has a specific format for us to represent the board. For 4 queens example, these are the 2 valid solutions. And here, we denote not the first square on the first row is not occupied, the second square is occupied by a queen, the third one is not occupied, the fourth one is not occupied. And on the second row,
Now, obviously, I don't think I'll be able to like resolve it right now, but I guess algorithmically, how would you check whether? Okay, let's move backwards now that we have the template. Okay, I'm just gonna guess the solution here, and then yeah, let's see. So I guess one way to check if a state is a valid state is to check whether, well, actually, you know what? Let's just go back here. I guess let me actually illustrate this. Just create a new file, call it nqueens.py. So I'm gonna copy over the valid solution from here. All right, okay. So let's just have them on separate lines so it makes sense. If this were a table, a state would be valid if and only if each column contains one queen and one queen only, right? Yeah. No, that makes a lot of sense. But no, actually that doesn't make sense. Because what if the queen was, we had some, oh actually I'll just copy it over. Because if we have something like this, then by our definition this would also be a valid state, but I mean this would not by our logic this would turn out to be a valid state, yes, but this isn't in reality, is it? Because this queen can attack this queen. So I guess we need to check we also need to check columns in a way, right? So we also, not only do we need to check the rows, but we also need to check each so not only do we need to check each column, we also need to check each row. And what about diagonals in that case? Can I find any possible combination where the diagonal, like the state is not possible just because of a diagonal? Huh. That's a question to give thought to now. I want to say no, but I can't intuitively the answer is no, but hmm, I guess that's how she's gonna do it. Just check the rows and columns, because maybe I can't explain it with a 4x4 board. So let's just add make this 6x6 board, and let's see what a possible solution would look like. here. Um, oh, actually, if this is a 6 by 6, we need to have two more such rows, right? Yes, we can't place that in there. Then placing this here, we place this in here. If we place this in here, we can place this in here. This seems to be a valid state. Or is it? Oh no, we have to check the diagonals also, because look at this. I know it's hard to kind of look at it with these dots and whatnot, but bear with me. This would turn out to be a diagonal. You can see that these two queens lie in the same diagonal. So I guess we also have to check the diagonal.
The first 3 squares aren't occupied, and the last one is occupied by queen, so on and so forth. And in the case where n is 1, the queen can only be on a single grid, so that's the solution.
So I guess we play around with indexes and check it out that way.
Before jumping into the code, let's first think about how we may represent this problem logically. We might be tempted to represent this board data structure as a 2D array, but it's actually a little bit waste of space to do so. Since this board data structure as a 2D array, but it's actually a little bit waste of space to do so.
I'm sorry, I didn't get that.
We might be tempted to represent this board data structure as a 2D array, but it's actually a little bit waste of space to do so.
Alright, okay.
Since no queens can be on the same row or the same column, we may just keep a 1D list that tracks the queen's position in each row. Concretely, for this example here on the left, for the first row, the queen is in the second cell, so the first index is 1. For the second row, the index is 3, since the queen is in the fourth cell. And this here is 0. This here is 2.
Ooh, okay. Oh, I see. Because if we use this as a state while returning the output, we can just, I mean, this is just string formatting, right? We can, yeah, that makes sense. So this would be what? This would be 2032. 2032?
Because
Oh, sorry, 2031. Yeah.
the third cell, the first cell, the fourth cell, and the second cell. So this is the way that we will represent each state as a 1D list for this backtracking problem. Now I'm going to grab my template and put it into the code. I'm going to move the solve method on top. As already mentioned, the solve method is basically the one that the code is asking us to write. So for the solve n queens problem, we will just be adapting the solve function. So solutions is initially an empty list because we may return all the valid solution in any order. Then my starting state is just an empty list because we haven't placed any of the queens into the board just yet. Then we call self.search on the state, giving it our list of solutions to append to, and the parameter n for the n queens. After the search is complete, we return the solutions. Let's go ahead and remove this part. Great. Now we will write the isValidState function. It will take as parameter self, state, and n. For state to be valid, it needs to put all n queens onto the board. So if the length of
Yeah, it needs to put all n queens on the board, yes.
for state to be valid, it needs to put all n queens onto the board. So if the length of the state is n, then we know we have already put all n queens onto the board. As for the condition where no queens can attack each other, we will handle it in the getCandidate function. Essentially, we will only return candidates that land on valid squares that won't be attacked by the previously placed queens. So self state n. Great. So here.
Oh, I see. Now this makes sense because if we have a state which has 4 indices in it and it came from get candidates, which ensures that queens don't attack each other, then yes, it's a valid solution and then we can just return it.
Here we are constructing candidates based on the state that we're given. If there's no state, meaning that we're starting from a blank board, we may place the first queen anywhere we want. So if not state, we return all the possible indices. If the state is not empty, we find the next position in the state to populate. So position is the length of the state. If we already placed the first queen, we want to place the second queen. So candidates initially starts from all the indices, and then we prune down candidates that aren't valid. I'm using a set because it's better than walking through a list, and set guarantees uniqueness. All right, let's prune down candidates that place the queen into attacks. So for row column in enumerate state, we discard the column index if it's occupied. So candidates dot discard. Recall that our state is recording the column index for each row. Now we discard the diagonals. So distance is the distance between the position and the row index. Because we're trying to put a queen in the second row, now that we have already filled in the first row, we want it in a place that cannot be attacked by the first queen diagonally. So this one is out of the question, and this is column plus distance. This one is also out of the question, column minus distance. And at the very end, we return candidates.
Okay, we need to walk through this. Okay. So far is valid state. Yes, it makes sense, right? What is a valid solution? A valid solution is a solution where the queens can't attack each other, and then we have placed all queens successfully on the board. Now, the logic in which no queen can attack each other is covered by get candidates. So if the state passed to is validate guarantees that, then we just need to check if len of state is equal to n. That makes sense. I agree with that. Now let's move to get candidates. So let's go back here. Initially, state is gonna be empty. All right, it's gonna be an empty array, right? Because I mean, in the beginning, we're gonna start off with an empty board. So if it's an empty board, then we return range of n. So if n is 4, as in this example case, we'll return 0, 1, 2, 3. Basically, we're placing the queen here, 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 here. 0, 1, 2, 3. Like we're placing it diagonally. Alright. Then what are we doing? We're finding the next position in the state to populate. Position is len of state. I guess let's just continue and see. Maybe it'll make more sense afterwards.
We occupied. So candidate X between the second row, now that we have already filled in the first row, we want it in a place that cannot be attacked. States, solutions, and n. We just add it to the solutions and return. Otherwise, if we come down here, for candidates in self.getCandidates, and no longer wants us to output strings, And here we have is a list of column indices. So state. So here's how we convert our list of indices to this output string plus empty cells and direct. And here instead of solution append state.copy, we do state string. And state string is produced by self.state to string. All right, great. Let's now self.state to string state. All right, cool. Great. Let's now run the example code to see how we string state. Great. Let's now run the example code to see to string state. Great. Let's now run the example code to see how we did. All right, cool. Looks like our output is accepted. Let's submit and see whether we can pass all the test cases.
All right. Okay. I guess the explanation ends after this. So, or maybe it
We're looking
doesn't.
for backtracking problems. Next, we'll solve another LeetCode problem called the Sudoku solver problem.
All right. Okay. In that case, let's just go through the logical once more. I mean the code as such is there in GitHub. So let's just look into that. So let's see. Just try to understand this. So what's happening? All right. We already covered what is valid state does, and it makes sense. Now let's see what. Well, let's actually start from the beginning. Right? Because what happens when we invoke the solve and queens function? I mean, method. I guess it's a method since this would be a class. Okay. We have solutions. We have state, and we're gonna invoke self.search state solutions and then we're gonna return solutions. All right. Okay. Cool. State is gonna be an array. Solutions is gonna be an array, and in the end, so this array would contain all the possible states, which would be arrays of its own. So this would be a array of arrays, right? Wait, let's go into self.search. What's happening here? So the first state that we're gonna give it is gonna be an empty array, right? Now I could go ahead and use a debugger, yes, but I feel this would be a better way to learn. So this would be an empty array, right? Because initially you're gonna start off with an empty array, empty chessboard. So this is gonna be false, obviously. So we're gonna get the actual candidates. Keep in mind this is gonna be an empty array. Let's go to get candidates. So initially, since it's gonna be an empty array, we're gonna place all the queens diagonally. I'm gonna take the 4x4 case here. Right, so this is what we're gonna do, right? We're gonna place all the queens diagonally because that's what return range of n returns, right? It will return these in indices. Actually, let's just you know what? I know this a bit of a again another detour, but to rel of index in programming, okay? Indexes, but it can also be spelled indices, okay? Oh, hey there. Oh yeah, it's pretty good right now. It's good weather indeed. I mean, nice weather indeed. How are you? Doing some DSA problems here. Oh, great, amazing. Oops. I believe you were there in the last stream or something also, right? 6:35 a.m. and it's already 6:35. Oh no, it's I actually have Linux installed in the same system, so it messes up the time. I don't need to fix it though. The actual time is what? It's 12:06. It's I guess you can say early afternoon if that's a thing. What time is it there for you? So let's see. 10:36 p.m. Oh, all right. You would be, I believe, you would be on the other side of the world. That's amazing. So doing some late night or watching some late streams late night. Oh, it's winter there. All right. I guess you want to use a emoji there, but it didn't work. Yeah, I mean, Indian summers do get very very hot, but it's not. It's not. It's sort of like I don't know. It's sort of like windrush summer where like summer hasn't actually begun. It begins in March, so it's kind of like a tropical climate, especially in the state I live. So it's pretty good. If I remember correctly, you said you were a developer, right? React developer or something. Yeah, right. I believe that's what you said. Again, I don't exactly remember, but or not React developer. Okay, was it web development? I believe it was web development, right? What do you develop in if not React? I guess some other Node.js. All right. Okay. Cool. That's amazing. You interested in DSA and stuff, or so? Let's just come back here. So yeah, as I was saying, basically initially we're gonna place all the queens in the diagonal. So obviously that's gonna be an invalid state, and let's see what's gonna come in next. Only in watching DSA. All right. I mean, I'm learning too, right? Like DSA is something which you know how I always wanted to kind of solve these very hard not lead code problems. I usually solve chord wars, and if you're not aware in chord wars, there's certain I believe they call it kata, right? Or Q levels, with one being the hardest. So I always want to solve them, but those problems require that like that their stuff which requires pure DSA knowledge. So yeah, I'm gonna learn as much as I can, and I want to be able to solve those problems one day. And I also believe it will help me, right, one way or another. Maybe when I make some AI projects or something. Also, I just like problem solving in general. All right. So let's come back. All right. So initially we're gonna place the queens in a diagonal. That makes sense. Now let's go back. What are we gonna do next? We're gonna find the next position in the state to populate. We're gonna take the len of state, which in this case is gonna be what? It's gonna be 4, right? We have occupied the board completely. Then we're gonna take candidates to be set of range of n. Huh. Set of range of n. I don't understand this part. How come this gives us a list of all possible candidates? Hmm. Let's just check here one thing here real quick. Set of let's do range of 4. Huh. Oh, okay, I see. Basically, we're creating we're trying to iterate through all possible rows. I believe that's what's being done here. Let's go back. So we get all the possible candidates, okay? Then we iterate through 4 row comma column in enumerate state. Hmm. What's happening here? Remind me, what was state again? Oh, wait a second. Okay, let's just come back to this again. So for candidate in self dot get candidates, initially this is gonna return that diagonal. Right, it's gonna return what? It's gonna return the set of numbers from. It's gonna return this. Now state dot append candidate. Right. So I guess state is gonna look like we're gonna. This is gonna be our first candidate, right? And we're gonna append the candidate to our state here. And then we're gonna call the self.search method on state solutions and then all right, so let's go back. Oh, we're gonna call this recursively. Okay, we're gonna call the same thing again, but this time when we hit self.isValid state, I mean, I guess still this is gonna turn out to be false, right? Let's look at what state is. This is what state is gonna look like, right? Mm-hmm. It's gonna return line of state equals n. Hmm. I don't understand why we're passing state in here, but let's just bear with it. So I guess that would be false because since this would equal 1. Alright, so this would be false. This one run, okay. And then we're gonna iterate, we're gonna call get candidates again, and we're gonna pass in the current state. This one run. And now what are we gonna do? We're gonna find the next position in the state to populate. Position, okay. Alright, since we're passing in state, position would be what? It would be 1. Candidates would be a set of range of n, which would, this would be our second candidate. For row, comma, column in enumerate state. Row, comma, column. So row is gonna begin at 0, right? Because that's what enumerate does, and column is gonna start at, so it's also gonna start at 0. Candidates to discard column. Discard the column index if it's occupied by a queen. Oh. I didn't exactly understand what that meant. Okay, let's just call discard here on what? We're gonna call it on 0. I guess we have to call it this way. Okay, it just removes. Just removes that. I mean, it just removes that. Distance would be equal to position minus row. So what is position again? Position is 1 minus row. Let's take a look at the. Let's take a look at another video to understand. I didn't actually understand it correctly.
Would you say yes to a software development job outside India?
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve n queen. So this is a pretty famous backtracking problem, and we're finally going to be solving it today. And this is marked as a hard problem, a solution, how we're going to apply the brute force method to get each valid arranged position we try. Okay, now let's try a different position, right, for the second queen. Let's try
I mean, he is doing this in Python. Yeah, he is.
Positions in the 4x4 grid. Let's put a queen over here. So that's the first position we try. Okay, now let's try a different position, right, for the second queen. Let's try putting the queen in this position, right? And then now we have all these remaining choices. Let's keep putting a queen in every single position and trying that. So this is one arrangement. Then maybe we could take the fourth queen and put it over here, etc., etc. Now, why is there any reason to do that? That's a little bit too brute force, if you ask me. There's a much simpler way we can do it. Right? Because for each queen, instead of having n squared choices, how about we just have n choices, because we know for sure each queen is definitely going to be in a different row. So first we can go like this. We can say, okay, we can decide to put, for this first row itself, right, this first row, we can decide to put the queen in the first position, or we could decide to put the queen in the second position, or the third position, or the fourth position. Whatever we do in that first row, then we're going to move to the next row, right? So now our goal is to find a different location where we can put the second queen in this second row. Now we could try putting it over here, or we could try putting it over here, or we could try putting it over here, but we can't put it over here. Why is it that we can't put it here? Because they're in the same column. So now you already can tell we're going to need to be maintaining the columns of whatever previous queens that we've already placed. We don't have to maintain the rows though, right? Because I just showed you why. Because every time we place a queen, we're going to move to the next row anyway until we get to the bottom, right? And then we're going to make sure that we're placing the last queen in a valid location, and if we are, then we're done, right? So we are going to have to keep track of which columns we place a queen in, and we're going to have to keep track of the positive diagonals that we're placing a queen in, and we're going to have to keep track of the negative diagonals that we're placing a queen in. And we can keep track of all of these with a set, right? So a set can tell us, a hash set can tell us which column of 0, 1, 2, or 3 we have put a queen already in, and we can do the same for a positive diagonal and a negative diagonal. But I bet you're wondering, how can we do it easily with positive and negative diagonals, right? We don't have indices for something like this, right? What index does this diagonal belong to? What index does this diagonal belong to? And I'll show you there's a bit of a pattern when it comes to diagonals, positive and negative diagonals. Let's say we start at the origin, the top left position, and then we go diagonally bottom right. So this is what
Mm-hmm.
I'm going to refer to as a negative diagonal because from left to right, we're end up going downwards, right? Do you notice anything about this diagonal? Well, we're starting at 0, 0, right? The row and column are 0, 0.
This is 1,
As we
1,
move
2,
diagonally
2, 3,
down,
3.
we get to this position, right? Then the row and column are 1, 1. Then we get to this position where the row and column are 2, 2. So notice how each time we're increasing the column value by 1 and we're increasing the row value by 1 as well. What does that tell us? That tells us along this diagonal, along this negative diagonal, the computation row minus column is going to stay constant.
And in this case, it's gonna be 0, yes. Oh, wait a second. What if we take another one? Let's take this. This 0 minus 1, negative 1. Oh, actually, let's do it the other way around. 1 minus 0, 1. 2 minus 1, 1. 3 minus... Oh, okay. Huh. Alright, okay. I agree, that's gonna stay constant.
Over here, right, in this position, if you take the row minus the column, we get 0 minus 0. That equals 0. If you take the row minus column in this position, we get 2 minus 2. That equals 0. So we can define this particular negative diagonal as being the 0 negative diagonal. Let's try it out on a different negative diagonal to see if our pattern holds. Let's start over here at a different position, row 0, column 2, and we're increased position of long negative, the negative 1 diagonal. 1 minus 0 is positive 1. So I just to be the negative, we can see that this pattern holds. The negative diagonal along this is going to be the negative 1 diagonal. The negative diagonal along this path is going to be positive 1 because we see 1 minus 0 is positive 1. So I just drew out a few of the diagonals. If you want to visualize it, you can see this diagonal is constant, this diagonal is constant, this diagonal is constant, etc., right? So that's how we're going to be doing negative diagonals. Is there a similar pattern we can use for positive diagonals? Let's see. So let's say we started our positive diagonal over here. We can see the row is 3, the column is 0, and then we go diagonally top right? We go up in this direction. Now notice when we do go in this direction, we're moving to the right. We're increasing the column by 1, but we're decreasing the row by 1.
So adding these two would always equal 3. 2 plus 1, 3. 3 plus 0 is 3. Oh, okay.
So we can't use constant. Over here, the row minus column is going to be 3. Over here, the row minus column is going to be 1. So it doesn't work if we do row minus column. But notice, since we're increasing the column going in this direction, but we're decreasing the row, that means row plus column is going to stay the same, right? The sum of these two values is going to stay the same because we're decrementing one, but we're increasing the other. For example, in this position, row plus column is 3. In this position, row plus column is also 3, right? So it's going to be 3 all the way. What about this diagonal? Does it also work? Well, 3 plus 1, that's 4 in this position. 2
4
plus 2, that's 4.
There's also
and this
4.
is also going to be 4. So you can see positive diagonals can be determined with R plus C. Turns out that these 3 sets are the only information we need. Then we can brute force start placing queens. How's the algorithm going to go? Like I mentioned, we're going to try each of the 4 positions in the first row, right? And for each of them, so the decision tree is going to look something like this, right? We'll try a queen in position 0. We'll try a queen in position 1, position 2, position 3, right? And this is all for the first row, and we'll do the exact same thing continuously, right? For if we put a queen here, then could we then we're gonna try a queen in all the other 4 places. So 2, 3, Now, if we placed a queen here, that means we put a queen here. So then could we put a second queen in the same column? No. That's how we're going to know. How are we going to detect that we can't do this? We're going to see that a queen has already been placed in the same column set. So we're not going to do that, right? So we can't place a queen here. What about position 1? Well, it's clearly not in the same column, right? Why shouldn't I be able to place a queen over here? Well, it turns out that it's already been added to the negative diagonal. This position means the negative diagonal is 0. Row minus column is 0. So this position is also row minus column 0. That means the negative diagonal has already been used. So we also can't put a queen in this second position. So this path in our decision tree also does not work. Can we put a queen over here in this position? Yes, we can. It doesn't overlap with the positive diagonal, and it doesn't overlap with the negative diagonal, and they're not in the same column, right? So we can continue this one, and we can also continue in this one, right? It's also not in the same positive or negative diagonal, also not in the same column. So that's kind of how the algorithm is going to work. I'm not going to draw out the entire decision tree because I think you probably get the point. These 3 sets are going to give us all the information we need. Okay, so like I mentioned, the 3 sets are going to be all the information we need. We have a column set, we have a positive diagonal set, and remember the positive diagonal is determined, let's just place a comment, is determined by R plus C, and the negative diagonal is determined by R minus C, so let's just make sure we remember that when we're actually writing our code, R minus C for the negative diagonal. And we're going to have a result, which is basically going to tell us all possible n queen solutions. And we're also going to maintain a board. So initially, I'm just going to make the board a array of, let's say, and by the way, I didn't mention this, but a dot is basically indicating an empty location. So this multiplied by n is going to determine a row. How many rows are we going to have? Well, for I in range n, right? It's an n by n board. So I'm just initialing a board with periods or dots in every single position. So then we can define our backtracking recursive function. And remember, we're going to be doing it row by row. So initially we're going to start at row 0, then we're going to go to row 1, row 2, all the way until we get to row n. Row n is our base case. That means
We'll come back to this solution here, but the explanation makes sense. Now let's just go back to this solution and see if this makes more sense now. So I guess that's what call plus distance and call minus distance does. All right, so let's come back. I'm just gonna copy this. We'll code it on our own, yes, but let's just copy this over for a second. So let's see here. Oh, I guess we also copied the template again. So let's just import. Let's fix this. Wait, so let's see. So we're gonna call solvent queens. We're gonna set solution and state to be empty arrays. Then we're gonna hit self.search. Okay. State solutions n. Now we're gonna check if the state is a valid solution. It is not a valid solution because it is gonna be empty array. Alright. So we just neglect this. We come here. Then we're gonna invoke the get candidates method. And we're gonna pass in the state and n here. So let's go to get candidates. If it's not state, which in our initial, since in the initial call it's gonna be an empty array, we're gonna pass an empty array here. And then let's see. You know what? I'm gonna take a 5 minute break and I'll be right back. Right, catch you in 5 minutes. Alrighty, I'm back. That definitely took more than more than 5 minutes, but here we are. So let's continue. Oops. Let me hit start there. Alright, so let's see. So we were about to walk through the problem here again, right? So where were we? Yeah. So state initially would be an empty array. So we're gonna return this, right? We're gonna return range of n. That's gonna initially look something like this, right? If n is 4, it's gonna look something like this. All right, good. Well, I guess list of range of n would look like this, but you get what I mean. Once we return this in, let's see, get candidates. For candidate in this, so again, what is get candidates going to return? It's going to return this list here. Or is it? Let's just check. Yeah, it's going to return that. So for candidate in this, we're gonna state.append candidate. So if this is our state, we're gonna return what? We're gonna append 0, and then we're gonna search state solutions. And is this how it's gonna work? State is gonna be an empty array, yes. Then we're gonna search for this thing again. State would be this array here, solutions, and you have an. So let's go back to search again. Is this a valid state? No, this is just has what, one element in it, so it's not gonna equal n. So it's gonna be this is not gonna be run. So it will move on to this again. For candidate and self.get candidates, we're gonna pass in this now. We're gonna pass in this, and n would obviously be still 4. We're gonna go to get candidates. Yeah, now this time, this is what the position is gonna be. The position initially for array containing 0 would be 1. Candidates would be a range of 1, so it's gonna be 0. Is that right? Set of range of 1 is just gonna contain 0 in it. Yep. Prune down candidates that place the queen into attacks. Okay, so for row comma column in enumerate state, so basically 0 0, discard the column index if it's occupied by a queen. Candidates to discard column, so it's gonna be an empty array. Distance is equal to position minus row. 1 minus row is 0. Candidates to discard column plus distance, column minus distance. Okay, I have to use a debugger to understand this, so let's just do that real quick. And let's just do l.solvent queens, and we can give 4 in there. And let's run this in debug mode. Now let's see. So what is state right now? It's empty as expected, and n is 4. This is going to return false. For candidate and get candidates, if not state, we're going to return this. Right? So, actually, you know what? Let's just have candidates here so we can look into what candidate says. All right, let's look at what candidate says. And okay, so 0, 1, 2, 3, that's what candidate's gonna be. Oh, now this should be, let's just remove that. All right, bless me. I guess, all right. Let's go back in again. It's gonna be 0. Okay, we're gonna append. So state was empty so far. Now we have appended 0 in it. Okay, we're gonna call search again. Now, what does this mean? What does the current state look like visually? This means that in the first row, we're placing the queen at the first square, right? So if I edit this, it's gonna cause issue in the debugger. So I'm just gonna, edit it in template.py. So currently the state looks something like this, right? This is what we're passing. So we have a board where we place the queen at the first square of the first row. Now we're gonna call search again. Why do I keep sneezing in streams? Okay, let's see. So this is our state and this is our end. Now, is this a valid state? No, because we need to place all 4 queens here. So we're gonna not run this. We're gonna get all other possible candidates again. Now, this is the logic which we need to kind of unravel. So position is gonna be what? And now state. Okay, all right. Find the next position in the state to populate. It makes sense because we have already placed queen on the first row. Now we have to place one on the second row or the first index, right? That's why position is 1 here. Candidates is gonna be zero. Oh, okay, yeah. Yeah, basically the candidates, what is candidate? It's basically the number of all the squares where we can put the queen in the second row, right? So since the board is of n squares, we can place the queen on either, let's go back to template, we can place it in the 0th index, first index, second index, third index of the second row. All right. Okay, that makes sense. And we're enumerating, right? Let's see for row comma column. So this is gonna be 0 0 1 1 2 2 3 3. Is that right? Row is gonna be 0. Okay, let's just try to understand this. Now, what is row and column? Gonna be 0 0 1 1 2 2 3 3. Now, these are candidates and we're going to discard 0 immediately. Discard the column index if it's occupied by a queen. Oh, wait a second. We're enumerating state here, not candidate. So, state is going to be this, right? This basically tells the script that, hey, there's a queen already in the 0th index of the first row. So, this card, you can't possibly place it. So, if this is a candidate, then just remove it. Because in this row, you can't place the queen in the 0th index. It's just not possible because the queen can move horizontally, vertically, and diagonally. So this takes care of the vertical part, I guess. Right, that's gone. So now what are the possible candidates left? We're left with, we can either place the queen here, here, here. Alright, now we're calculating something called as the distance. Now what is that? The distance in this case is position minus row. Okay, if this were the coordinate, like the coordinate system, then this point would be what? It would be 0, 1, right? But I guess if this is the origin, then I guess this should be the origin for that to make sense. But yeah. Okay, let's just see what's happening here. So we calculate position. So this is where the neat code logic that was explained comes into play, right? Let me actually go back to that video. Let's see. Is this the one? Yeah, this is the one. So basically,
join us for the biggest
alright,
competition with over $10,000 in cash prizes.
We'll try a queen.
Alright, so basically, this is a negative diagonal, right? If we add the two indices, it's gonna be a constant, right? So if we subtract both indices, it's gonna be a constant. 0 minus 0 is gonna be 0, 1 minus 1, 1, 2 minus 2, 2, 3 minus 3. So 2 minus 2 is 0, 3 minus 3 is 0. So this entire negative diagonal has a constant of 0. In fact, you know what? Let me take a whiteboard here. Maybe how there's a electronic board thingy. Maybe I can buy that, and that might be useful, because me writing with mouse is gonna be it might just be legible to me, so we need to look into that. But right now, let's just create okay, 1, 2, 3, 1, 2, 3, 4. Right. So let's just write 0, 1, 2, 3 here. 0, 1, 2, 3 in here. Now, let's calculate the negative indices, right? Should be 0. 1 minus 1 is going to be 0. 2 minus 2 is going to be 0. 3 minus 3 is also going to be 0. 1 minus 0 is going to be 1. 2 minus 1, 1. 3 minus 2, 1. Right? And what is this going to be? Negative 1, negative 1, negative 1. I think you get the point here, right? 2, 2, negative 2, negative 2, and so on. All right. Similarly, in fact, can I zoom out here? Let's just calculate another board. Can I copy this? There a way? I guess, yeah. Let's just create a new one. So we have 1, 2, 3, 4, and then we have 1. That one was 1, 2, 3, 4. Let's calculate the positive diagonals now. So, what's that gonna look like? So for this, we can see that, let's take this. 3 plus 0 is gonna be 3. 2 plus 1 is gonna be 3. 1 plus 2 is gonna be 3. 0 plus 3 is gonna be 3. Similarly, this is gonna be what? It's gonna be 2. 1 plus 1, 2. 2 plus 1, 3. 2 plus 0 is gonna be 2. Similarly, here it's gonna be 1 plus 3, right? That's gonna be 4. 2 plus 2, 4. 3 plus 1 is gonna be 4. Then 1. We have this. 1, 0 is gonna be what? 1, 1, 0 is gonna be 1. Then we have 2, 3 is gonna be 5, and we have 5 here. That's what the positive indices are gonna look like. I mean, positive diagonals are gonna look like.
Queen in position.
Why did I, go through this again? To understand what's happening in here, right? Basically, we're gonna discard column plus distance. Now, what is column plus distance? Let's just check that out. Distance is position minus row. Let's try to understand what's happening here. What does position minus row give us? Let's try to understand it. Now, what is position? Position is the next, let's see, the next index row, right? Trying to go into, yeah, there we go. Can I open this side by side? Yes, I can. So, in a way, I guess, position, oh, wait a second. Oh, all right, there we go. So, position is basically the row index, right? So the first row is gonna be the next row that we need to place the queen on. So that's what position is gonna be. It's basically in a way the y coordinate, right? And then we're subtracting row from it. Now, what is row? I see what's happening. So how far is this row from the row that we're calculating for? So in this case, that's gonna come out to be 1. The distance is 1 between these, right? And here it's gonna be 2. Here it's gonna be 3. That's what distance means. All right, that makes sense. Now, what about this? We're adding column plus distance. Why are we doing this? Try to understand. So state gives us the current column that we're on, right? So currently we're on the 0th column. Yes. Okay. Column plus distance. Wait, what does column plus distance give us? Does it give us the negative index? I mean, sorry. Yeah, I guess what I'm trying to say is this. Let me open up the whiteboard again. And column plus distance gives us what? It gives us 1. It's trying to, but this is not a diagonal, is it? Oh, wait. I guess column plus distance doesn't make sense for this square because there is no, there's no, we're not positive diagonal here. Is that the reason? But negative diagonal makes sense. It will be 0. So I think that's it. Okay, let's just keep that in mind and just move forward. So this should remove that removed removed 1, right? Okay, what about, so this tells us, hey, you can place the queen either in here or here. All right, we're gonna return the candidates and let's see. For candidate and candidates, we're gonna append the candidate. Let's look at our state right now. 0, 2 is a possible combination. Okay, we're gonna calculate this now. Let's just copy this over first. Put a queen over here. Then I'm gonna hit search. Let's see. Now we're gonna calculate the possible candidates again. the position this time is gonna be for, we have to calculate where we can place the queen for the second, I guess the third row which has index 2. For row column in this, let's look at this state again. Now this time when we check where we can place the queen, we have to evaluate it for both this queen and this queen. That's why we're evaluating it for this and this. Let's check our column. Let's look at our candidates again. Yeah, I mean, candidates is always gonna be like these 4 columns. And first and foremost, we're gonna remove the column because, yeah, if you're calculating for this, you can't place a queen on this 0th index. So we're gonna remove that. Done. Candidates is gonna be 1, 2, 3 with regards to this. Distance is gonna be position minus row again. And this time, okay, let's see what column plus distance gives us. It gives us 2. Now, why can't we place a queen on the second one? Because it falls in the negative diagonal, right? So this column plus distance is, in a way, I mean, not in a way, it's trying to calculate whether the, queen can be placed in this diagonal, and it can't, right? So it's going to disregard that. So our candidates is going to be basically 1 and 3 here. Now, column minus resistance again doesn't make sense because this, it's it the queen is in the, like, there is no positive diagonal here. So let's check for the second queen. And again, so obviously we can't place a queen here, 0, 1, 2, but there is no 2 here anyways, since it isn't possible for this queen like the same diagonal, so it removed it. Now the distance from this is going to be 1. Similarly, we're going to check whether, well, first we're going to check the column plus distance, positive diagonal. I mean, sorry, negative diagonal, right? Because what's the negative diagonal going to look like for this? Not. Oh, I think I'm overcomplicating it. The solution doesn't depend on that logic entirely here. It's just, in a way, it's just checking whether the, like, what is column, right? The column is the place where the current queen is on. The current queen is in here. Obviously, you can't place a queen here, right? To the next index. You can't place one here. Not gonna work. You also can't place one to the left hand side. In other words, subtract the column minus distance, right? Oh, shoot, this one. And you can't place one here also. I was just overcomplicating it. It's just, I mean, in a way, yes, it's sort of using the logic from NeetCode, but it's not. Yeah, we look at the solution from NeetCode again, but this is much simpler than that, isn't it? It's just checking whether, it's just disregarding the possibilities of the queen being to the right hand side of whatever state you're calculating for, whatever queen you're calculating for, and similarly to the left hand side. And obviously, the same column. That was a mouthful, but that makes sense. And this time the candidates is gonna be, it's gonna be empty, is it? Or yeah, it's gonna be empty because this, you can't place a queen anywhere in the third column now. Now we're gonna state.pop, we're gonna remove 2 because that doesn't work. And we're gonna run this thing again. And this time let's check. We have 0, 3, 1. Okay. So basically we have 0, 3, 1. Right? So far so good. We need to come back here again. Just come back to this state here real quick. Let's just put a state equals 0, 3, 1. All right, cool. So if you look at this state now, we're back at 0, 3, 1, which is this. Now let's look at the candidates again here. Where can we place a queen? We can't place it here. We can't place it here. We can't place a queen anywhere, right? This is, so we're gonna pop out this again. So the state is gonna, we're gonna come back to this combination here. Actually, you know what? We'll just, right, this is what we're gonna do. Gonna come back to this combination. I'm gonna retry again because last time we checked the combination with what? Oh, I guess this would be a new candidate. Huh. All right. Anyhow, let's just hit search. And this time, what does our state recommend? It recommends us to go with 03. Why 03? I guess because yeah, we extinguished every possible candidate here, right? This simply wouldn't be a possible solution. So we're gonna remove that again. And then we're gonna get 0. Okay. So again, we're backtracking. This wouldn't work. We're gonna come back. And what? Okay, we'll remove this too. Now we're gonna place the queen here, I guess. Let's just print this and see what it returns first and foremost. Huh. Yeah. But you know what? I have sort of understood what the in Queen's problem, like the approach that is taken by this solution over here. It doesn't show in a way, yeah, the negative diagonal, positive diagonal logic is applied, but Most we're just checking whether the queen can go here, or here, right? So yeah, it's just checking whether the queen, you're trying to place the queen like to the right hand, like just very close to the queen. If so, you can't obviously have that. So I'm gonna look at this again tomorrow. Obviously, we have not completed this by any means, but we're gonna look at it again tomorrow. We're gonna sort of run through this again, and then hopefully we finish the end queens problem by tomorrow, and then yeah. Yeah, I guess this was the beginning to our backtracking or problem solving segment of the stream, and in a way we have covered backtracking. Now I'm not gonna commit this yet because it's just, yeah, it's not ready to be committed yet. So just gonna keep it as it is, and we look at this tomorrow. All right, cheers everyone. Take care. I'll see you in the next one.